We're now going to discuss the nitrogen equivalent of the acetal formation. Now, there turns out are two different nitrogen equivalents of this. We're going to discuss just one of them in this chapter, and we're going to save the other one for a different chapter. In this case, our observed reaction looks like this. We're going to start with a ketone or aldehyde. We're going to treat it with H2NZ. Now, Z is just a placeholder. It's some other group that is attached to the NH2. We're going to see that there are a variety of different potential Z groups that could be used. This creates a variety of different similar functional groups. I have a chart of that down below. So we use H2NZ. Again, we use our aqueous strong acid. What we observe in this case is very interesting. We get, instead of a C double bond O, we get a C double bond N. And the Z group is still attached, but the two hydrogens are gone. Now, to get this overall result, we have to have two hydrogens on the nitrogen. Always have to have an NH2 to get this result. Later on, we're going to study a reaction where there's only one hydrogen on the nitrogen, and we'll see that that goes in a different direction. Okay, when we have a C double bond N, when we have two bonds between a carbon and the same nitrogen, very often the names are going to have im in them. And so we're going to see that down below. This is a chart of just a few of the common different Z groups that can be attached to the NH2. And when we do that, we create different functional group products which have different names. Now, I am not actually going to require you to memorize these names, and I'm not going to test you on these names. I do want you, however, to be able to deal with potentially having different Z groups attached. So just really quickly going through here. Most common one that we would be interested in is the one where the Z group is either a carbon group or a hydrogen. In that case, our H2NZ is actually called an amine. The product is called an imine. Notice how the A becomes an I when it becomes two bonds. And we get this, C double bond N carbon group. Turns out the Z group could also be a hydroxyl group. This is called hydroxylamine, and the product is called an oxime. It can be another NH2 group. Our reactant is called hydrazine, very toxic, somewhat explosive, used as rocket fuel. When we do this reaction, the product has C double bond N, NH2. It's interestingly called a hydrazone, which is sort of like a hydrazine ketone or something like that. And then finally, we can modify the hydrazine by adding carbon groups onto the second nitrogen. And in that case, for example, if we use a phenyl, we get phenyl hydrazine, and then we get a phenyl hydrazone. And these we are going to use in lab when we do qualitative analysis. They're often used to make stable, solid derivatives of ketones that we can melt and identify. Okay, so here's our mechanism. I've sort of crossed out a typo here. So I had RNHZ, that has only one hydrogen. We need to have H2NZ here. So I crossed those out wherever I could and fixed it. Okay, so now if we look at how the structure changes, let me go back up to our observed reaction. We can see that we're really doing two things. We're adding a nitrogen and we're removing the oxygen. So this basically implies two overall phases, right? Add the nitrogen in the form of H2NZ and then remove the oxygen. So phase one will look like this. Protonate, add, make stable. The only thing that's different between this and acetal is the identity of the nucleophile that we add. So we protonate, we get our protonated carbonyl, very reactive toward nucleophiles. We have our H2NZ, the nitrogen having a lone pair, comes over and makes a bond. We create our intermediate here, which has a positive formal charge on the nitrogen, makes it kind of unstable, like to be more stable, so we deprotonate that, and we get this, where we now have an OH and an HNZ attached. Now, to complete this reaction, we would like to remove the OH. We already discussed how to remove an OH. We protonate the OH oxygen in order to make it more like a water, which is a more stable leaving group. We remove the water, get this intermediate. This intermediate has resonance, very similar to what we saw earlier. But when we do resonance here, we can actually make this intermediate where nitrogen has a positive formal charge more stable by deprotonating it because we have another hydrogen attached. So we deprotonate and we get C double bond and Z as our product. Very much similar to the acetals, this C double bond N formation can be converted backwards to the original carbonyl and the amine using hydronium. Mechanism is the exact reverse mechanism of the one we just wrote. You should practice writing that. We're next going to discuss a couple of other reactions of carbonyls. These are going to be classified into two groups. One is a series of reduction reactions. The other one is going to be just a few oxidation reactions that actually only occur on on aldehydes. Okay, so hydride addition. This is a review reaction from our chapter on alcohols. I'm going to go fairly quickly, but I do want to kind of touch base on this. We have two observed reactions. We start with a ketone or aldehyde. We can either use this substance, sodium borohydride, NaBH4. We generally use that in pure methanol. At the end of the reaction, we've added a hydrogen to the carbonyl carbon. We've also added a hydrogen to the oxygen. We call this a reduction for two reasons. First of all, we're moving from 2 bonds to heteroatoms to 1 bond to heteroatoms. The other reason is that we're adding bonds to hydrogen. So anytime we add bonds to hydrogen, that's also a reduction. We have a similar reagent using aluminum. Start with our ketone or aldehyde. We do this in two separate steps. Lithium aluminum hydride, LiAlH4. Then in a separate step, we add hydronium. We have to do two separate steps in this case because lithium aluminum hydride will react kind of explosively with water if we mix them together. At the end again, we get hydrogen added to carbon, hydrogen added to oxygen, only a single bond now. Now we're going to discuss what I call a formal mechanism. The formal mechanism is not the quote-unquote actual mechanism. What we're going to do instead is use sort of an abbreviated or an imaginary species to sort of envision what's happening, okay, even though that species doesn't really exist. So what we do is we imagine that sodium borohydride or lithium aluminum hydride give us this species right here. Hydrogen, 2 lone pairs negative. So hydrogen negative would be called hydride. You'll notice I put it in quotation marks because we actually don't ever get hydrogen negative by itself. Turns out that ion is just too unstable. It always is associated with some type of counter ion or covalently with some type of very low electronegativity atom. But the interesting thing is these substances react as if they were hydrogen minus. So for example, we take our hydrogen minus, it's a nucleophile. If we imagine this pair of electrons can come over and make a bond to our positively charged carbonyl carbon, we push a pair of electrons out of the way. we would get this intermediate right here. Now, this is a tetrahedral intermediate, but since we're using an aldehyde or ketone, we have only carbons and hydrogens attached. And so now there's not sufficient electron pressure to push out one of these groups. They are too unstable. So we stay like this, O minus. The O minus then will now seek to become protonated so that it can reduce its negative charge. So if we're using sodium borohydride, we have methanol, we have a large excess of methanol. So eventually one of the O minuses from our product will grab a hydrogen off of a methanol. That will make a CH3O minus, but since we have a large excess of methanol, equilibrium will favor protonating this. In contrast with lithium aluminum hydride, we're sort of stuck like this O minus until we add hydronium, in which case then we just do acid-base reaction and we protonate. The other thing I want you to recall is that sodium borohydride is the weaker of the two, and it only reacts with ketones and aldehydes. Lithium aluminum hydride is much more reactive. It will react with aldehydes and ketones, but it also reacts with esters, carboxylic acids, amides, and nitriles, which are observed reactions that we're going to discuss in a future chapter. The second reduction reaction I want to talk about is adding organometallics, adding carbon groups. Generally, we use Grignard reagents, although we can see here, we can also use alkyl lithiums for this. This again is a review reaction from last semester. We start with a ketone or aldehyde. We treat it with Grignard reagent, which would be RMgX, where X is Cl, Br, or I. We do first the Grignard, then we do a separate hydrolysis step. The Grignard has made a bond to the carbon of the C double bond O. It's converted it to a single bond, and then we protonate. So we make an alcohol. We do a similar thing with an alkyl lithium, RLi, or R minus Li. Again, hydronium second step, whatever. This is a pretty straightforward mechanism after looking at the heteroatom exchange reaction mechanism. It is, however, a formal mechanism, which I neglected to put up here. The Grignards are very interesting, alkyl lithiums and Grignards, because the bond between the metal, the magnesium and the carbon, or the lithium and carbon, is an extremely polar covalent bond, just on the verge of being ionic. However, it is not truly ionic because we don't really observe a situation where the metals and the carbon negatives can move independently of each other. They seem to always be kind of stuck together. However, the carbons do behave as if they were just really strong base carbon minuses. So what we're going to do is we're going to imagine them as such in order to help us visualize the reaction. So therefore, we're going to write R lone pair negative, quotation marks. This lone pair then would be attracted to the carbonyl carbon, would make a bond, we push a pair of electrons out away. Again, we get a tetrahedral intermediate. Again, that tetrahedral intermediate is stable because there's no heteroatom groups available to push out. Therefore, the O minus will at a later date, be allowed to react with hydronium. We'll put in hydronium, it will protonate, and we'll get our product. Grignards and alkyl lithiums are pretty easy to make. I'm going to show you the reaction for Grignards. We start with an alkyl halide, so carbon attached to chlorine, bromine, or iodine. We put in magnesium metal, which we symbolize with the 0 charge. Magnesium metal, therefore, has 2 electrons that it would be willing to give away so that it can reach the nearest noble gas configuration. So if it gives away those 2 electrons, it becomes magnesium 2 plus. Those 2 electrons, interestingly enough, are going to go onto the carbon. So it first puts 1 electron into the carbon. That causes the X minus to break off as a leaving group. Then it puts in a second electron to fill it up, give it a complete octet. Now, Grignard reagents and alkylithiums are excellent reagents. However, they do have one problem. They are very strong bases. And so if we put them in with anything that is even a moderately weak acid, they're going to do acid-base reaction instead of doing carbon addition. So they will readily deprotonate any OH that we present, any NH that we present, SHs, PHs. So we can't have those bonds in our molecule if we want to do a Grignard addition. So OH, NH, SH, or pH can't be present in the Grignard reagent or in the carbonyl. Otherwise, something different is going to happen.